Hi guys, welcome back. We're going to cover section C in chapter 5 today, and there's kind of a lot going on in that section. So here we go. We're going to talk about how to name different compounds and how the formulas work. And we've talked about this a little bit. So these chemical formulas include the symbols of an element and these subscripts. Okay, let me grab my pen here. Now, it's important to know that the symbols have both capital letters and lowercase letters, and it's really important to follow that because otherwise you get a little, mixed up with the different elements. So for instance, that capital I, that would be chlorine and iodine, whereas the lowercase l is chlorine. And so carbon and iodine, sorry. Not chlorine and iodine. Chlorine and iodine would be Cli. And so it's important to maintain those capitals versus lowercase, okay? The subscripts are what indicate the number of atoms for each of the molecules, and it shows the ratio of atoms. So for H2O, that means there's 2 hydrogen atoms and only 1 oxygen atom. So it's a ratio of 2 to 1. If there's only 1 atom, you don't need to put a subscript 1. It's kind of like math where if you have 1x, you can just write x, okay? Binary compounds are those that only have 2 elements. So water would be a binary compound, bi meaning 2. And then these elements, we've been talking about this a lot. These elements make compounds depending upon the number of valence electrons. Remember, they're trying to get that magic number 8, that rule of that octet rule, okay? Now, there's some rules with naming. Now, these are ionic compounds. We always start with the cation, that's the positively charged ion, and then follow it up with the anion, which is the negatively charged ion. Now, because of the way the valence electrons work, the cation typically is on the left side of the periodic table, and the anion is typically on the right-hand side of the periodic table, and so they kind of are in order that way. You need to make sure that's the case, though. And then we change the ending of the anion to end in this IDE. So instead of sodium chlorine, we call it sodium chloride. And you can see in this list here some common elements, some common ions with that "ide" ending. If you look on page 110 in the book, it shows you sodium and fluorine. Okay, fluorine is right there next to oxygen. Sodium has 1 valence electron. Fluorine has 7 valence electrons. So fluorine is very similar to chlorine. Now, when they're bonded together, we don't call it fluorine, we call it fluoride. And so once those electrons are transferred, the anion takes on that IDE ending, and so we would call it sodium fluoride. Okay. Here's some other naming examples. We've got sodium and oxygen, okay? Sodium has 1 valence electron still. Oxygen has 6. So the oxygen needs to gain 2 additional electrons. And so you're going to actually find it with 2 atoms of sodium, okay? Because each will give 1 electron. So the final formula would be Na2O, implying 2 sodium and only 1 oxygen. It's the same ratio as water there, okay? You can see that there's a double bond. We're not going to do the dot structure right now, though. We're just kind of talking about the ratios and the naming. If we look at magnesium and nitrogen, they get a little more complicated. Magnesium has 2 valence electrons to donate, okay? It only has 2, and so when we have less than 4, they tend to give them away. When we have more than 4, they tend to gain them, okay? Nitrogen has 5, so it needs to receive 3 valence electrons to hit that magic 8, okay? Well, if magnesium, if 1 atom of magnesium donated 2, that means nitrogen still needs 1 more, okay? Sorry, it needs 3 more. So we use 2 atoms of magnesium, and now there's 4 valence electrons being transferred. That's an extra 1. So we haven't balanced things out, okay? So what happens is we have to come up with this lowest common denominator between the atoms so that it works itself out, okay? So ultimately what happens is we get 3 of the magnesiums giving a total of 6 electrons. And then we've got 2 of the nitrogens, which needs 6 electrons, okay? So 2 times 3 is 6, and then that 3 times 2 is 6, and so we've equaled it out, and so that's why we get the MgN right there. I pointed out that double bond earlier. That actually goes with this compound, not the one up here. Duh. Okay, let's talk about these polyatomic ions. Poly means many, and so this is a group of atoms. They're covalently bonded together, but they really act as a single ion. Okay, so they're covalently bonded, they become charged, and they stick together. And it's almost like it becomes its own element that then can combine with other things. I really don't need you to worry too much about these other than, let me move myself here. There we go. That these are some very common ones. Ammonium, carbonate, sulfate, phosphate, nitrate, and hydroxide. You can see the superscript now, super meaning above. The subscript is still doing the same thing. It's telling us how many atoms there are, but this superscript now is indicating the charge, okay? If there's just a plus with no number in front of it, that means it's a +1. If there's a just negative with no number with it, it's a -1. We do the number before the sign for some reason. The positive charges means that they have donated electrons away. So there's more protons than electrons. The negative charges means that they've accepted those electrons, so that jacks up the negative charge there. And aside from that, I really don't need you to worry too much about polyatomic ions. You'll learn a lot more about those in high school. All right, last thing in section C is the oxidation state. And if you look on page, this isn't the last thing, it's like the second to last thing. If you look on page 113, there's a table that shows the oxidation state of these elements. And there can be more than one oxidation state, okay? But there usually is one that's more common than others. The oxidation state is the electric charge gained or lost by an element when it forms a compound. And so it has to do with the transferring of these electrons, okay? And it usually has to do with the number of valence electrons, especially when we're talking about groups 1 and 2, and then 13 through 18 that we've been talking about this whole chapter. So the primary oxidation state, the main oxidation state, is related to the valence electrons. So if we look at this family right here, our alkali metals, those we know have 1 valence electron, okay? So their oxidation state would be +1 because what they need to do is get rid of that 1 electron, leaving them with a +1 charge. Right here, the alkaline earth metals, they have 2 valence electrons that they want to donate, and so that will leave them with a +2 charge. Then we've got, let's skip over to the halogens here. They have 7 valence electrons. They need to accept, they need to receive 1 additional electron, so that will give them a -1 oxidation state, oxidation number. The oxygen family here, they have 6 valence electrons. They need to gain 2 more, and so on, okay? Again, this has to do with bonding. The oxidation states kind of work together because they're constantly looking for that magic number 8, okay? All right, now this is really the last thing for section C. By the way, in section C, there's a ton of examples of formulas and namings. You should absolutely go through those along with this video. All right, so this is just some more naming tricks here. When we are talking about different numbers of atoms, we frequently use Greek prefixes to indicate how many there are, in addition to the subscript. This is used with binary covalent compounds. So not ionic, binary still means 2, okay? We don't use a prefix when there's only 1 atom. Sometimes we do, because we've got this mono right here, but we don't have to, okay? And we typically don't use this for the, well, no, actually we do. Never mind. I would say we don't use it for the cation, but we can. The examples I have here, we don't use it for the cation. So we've got CO. There's 1 carbon and there's 1 oxygen, okay? Now remember, the oxygen is the anion, so it's going to end in that IDE. So we would call this carbon monoxide, mono meaning one. CO2, same thing, carbon dioxide, di meaning two, okay? So here I've got boron and fluorine combined together, okay? Remember that anion is going to take on that IDE suffix there. So this is boron fluoride. Then we want to put a prefix on it to indicate how many. As we see that the prefix is tri. So this is known as boron trifluoride, okay? And it gets more complicated depending on how many actual atoms we have in the ratio. So there's a table there that shows you the different prefixes that can be used. And I believe that is all I've got for you. It is. All right. See you guys later.